Yeah. So welcome to the second talk of our workshop. I'm on this DC. Like right now, I'm in between positions. So until Friday, I'm in one place, and Monday I will be in another place. So yes, I'm going to talk about this online combinatorial options and allocation. Which in a sense is the version of the problem that Sahil described at the beginning of the talk, when you have few copies of each resource, or maybe one or this. Yeah, so let's start defining the model. You have a bunch of items, right? Sahil's talk was resources here. I think there are items that are to be allocated among a set of agents that arrive one by one, and they have valuations for the items. They live in some support, it's called B, and I assume they are monotone valuation functions. And importantly, these are not just one number, are a mapping from every possible subset of the items to a value, right? So whenever an agent arrives, we want to decide which items go to this person. I assume there is just one copy of each item in the entire talk. So when we assign an item to a person, this item is gone first, right? And we want to maximize the social weight. Now, if the sequence of agents is completely adversarial, then there's nothing we can guarantee in terms of social welfare. I mean, we have this very simple example. The first value could be 1, and we have to decide whether to allocate distinct values to this person. And the next day could be either 0 value or 10,000. So depending on what we do on the first day, we cannot guarantee anything, right? So we have to make some extra assumptions about the agent. Yeah. So throughout this talk, I will assume the valuations are independently drawn from distributions that are given to us beforehand. So we have a distribution of 1, a distribution of 2, and to n that are supported in this set B. Yeah, and whenever a person arrives, the evaluation is drawn from this distribution. This is called the Bayesian setting because it comes from the literature on mechanism design. But there are other, of course, other ways of getting around this adversarial input. You can think of random order. There is literature on that. Or you could make strong assumptions about the support, right? For instance, you could assume all values are either 1 or 2. And there, of course, you can get a 1/2 approximation to this. Here I will talk about this Bayesian setting where valuations are done. Again, this is the setting. We have the items, people arrive over time. I want to design an algorithm, an online algorithm that when a person arrives, observes the valuation of the I and decides which items are allocated to I. Let's call that alpha. So these items go to this person. Our objective, as I said, is to maximize expected social welfare, which is the expectation of the sum of the valuations for the item. And we compare against the optimal offline welfare, right, which is the expectation of the best possible partition of the items. And we say an algorithm is alpha competitive if the expectation of the algorithm is at least alpha times the expected optimal partition of the items. Yeah, so let's look at a small example of what an instance could look. Okay, so we have 3 items, these 3 fruits, A, B, and C. yeah, I really like TPP, everything. Anyways. So we have two agents. This is the support, these four valuations. So as I said, evaluation is a list of 2 to the n numbers, one for every possible subset of the items. We're given distributions. So a distribution in this case would be what the probability that the value is 1 is each of these elements in support, right? And then when people come, we observe some realization from this distribution, right? And we have to decide which items go to this person. So now we look at this list of numbers. Okay, we choose one entry here. We give these 2 items to this person for a value of 0.6. And then the next person arrives and we observe a realization from that distribution is this. Now we are left with item C. It's a value of 0 for item C. And the welfare of this allocation then is 0.6, the sum of these 2 values. And in hindsight, when we could have given all items to the second person for a value. So we want to maximize the expectation of what we get with the algorithm, and want to compare to the expectation of the algorithm. That's supposed to be. Now I want to talk about 2 different important techniques. There are more techniques, but these are the ones I like. One is using balance prices, setting a price for each of the items. And it's called balance because in a way it balances what we get from selling the items, like the revenue, and what we get from the utility of the agents, like the excess over the price. And then I will show you a result regarding something called D-demand valuations, which intuitively is valuations such that no one wants more than the items. So if you ask them like which items you want, and they always take at most the items. Imagine that the case. No one does agree with 10 legs, right? So yeah, that's kind of a reason to consider these D-demand valuations. And then I will talk about another technique, which is an idea of protecting items with something. So instead of using the revenue from the prices to balance things, we use samples to protect items from being allocated too early. So they are available when someone with high valuation happens. And yeah, that's very useful to work with other classes of valuations that I will explain in a minute. Okay, so to explain what the balance prices are, I want to start with the single item case, which is known as the property equality. So we have one item. The valuations is just one item and just one number, right? How much value they get from the one item. The classic result in this model says that we can get a 1/2 approximation with respect to the optimal allocation. And here is an algorithm. There are many algorithms that the system can have. Here is one using this balance price. We want to set a price that compensates for the loss in utility in the future. So if someone takes the item, we'll pay the price, but we might lose some value in the future. And then we want to set the price to compensate for that loss in the future. So we set the price, which you can think also as a threshold in this problem, right? So the price, the first person that arrives whose value is larger than the price, we take it. And let's call Q the probability that the maximum value is about this. Let's compute some things. So the revenue in this problem is just the price, right? If we sell the item, we get the price. And Q is exactly the probability that we sell the item, right? So the revenue is Q times. And what is the utility? I said the utility is the excess over P of the person that gets the item. Well, this should be an equality. So the utility will be, well, sum over agents of the utility of the agent if they get the item. So what will that be? Well, is the value minus the price. The positive part, because if value is lower than price, they don't get the items, right? And then times the probability that the item is available. And why times? Because notice that the event that the item is available when someone arrives is independent of this person's value, right? Because it depends only on the values of previous people, right? When I arrive, the algorithm hasn't seen my values. So this is the probability that the item is available for agent I times the expected value over the price. And then the probability that the item is available, we can lower bound it with the probability that the item is available at the very end. That means the probability that we never allocate the item, right? And this is exactly 1 minus Q, right? The probability that no one has value above the price. Now, I said I want to compensate with the price the loss in utility, right? So essentially what I'm saying is that I want to make this price, that price over there in the revenue, equal to what I would lose in utility, which I say is expected opt minus price. I want to make these two things equal. So I can take the price as half the expectation of opt, right? I make these two things equal. And now when I sum these two things, the Q's cancel, and we get expected opt divided in total, right? Perfect. So that's for a single item. How can we use this idea with more items? Well, if the evaluations are additive, then it's very simple, right? By additive, I mean the evaluation can be expressed as sum over items of a value for each item. I can split the instance into one instance for each item. I just take the evaluations to be the value for the one item. In each item, I get expected half of the expected maximum. I buy the negative of expectation and just get half in the entire instance. But I want to go beyond this additive world. And for that, I need to describe what I mean with beyond additive. Or what other things are there beyond additive. In this talk, I will consider these two types of assumptions regarding evaluations. On the left, we have the blue, it's called complement-free hierarchy. It's called complement-free because it models situations where there are no complementarities among the items. So I think of that as fruits, right? You go to the supermarket, you buy fruits. There's not really a strong complementarity between the fruits, right? If you go one day and the strawberry is cheap, you buy strawberry. If the blueberry is cheap, you buy blueberry. So, I mean, unless I want to make like fruit salad or something. Yeah, there are no complementarities. I will explain later when we go into that what some of these classes are, but this is the idea. There are no complements. On the other side is what we call demand of size D, which means that no one wants more than the items. Whatever the prices are, no one buys more than the items. All right. Especially an important case is D equals 1. That is called unit demand. I just want one item, the one I like the most among the ones that you offer me for the price. But you could think of wanting more. So imagine the following. Say you're going to a concert, you're going with 3 friends, right? You want 4 tickets. You don't want more than 4 tickets. You have different evaluations for the seats, but you don't want more than 4 tickets, right? So anything beyond 4 is useful, right? Another nice example is the case of LLDs, right? No one wants 10 legs in the trip, right? Everyone takes like 2 or 3 legs in one trip. So if the products are the legs in the trips, right? Most likely the all valuations are like of demand of size, right? Yeah, funny thing. I did a trip with like 6 legs to come here. I was last week in Greece. I went from Chile to Greece, then from Greece to here, and then from here I'm going back to Chile. Well, then I'm going to Switzerland, but that's a different story. I tried to book everything at once. The price was like $8,000 to have everything in one reservation. In the end, I would separate flights for the hurricane. But you see, I mean, there are situations where there are complementarities, right? I wanted all these things at the same time, and if I didn't get all of them, it was a problem for me. So, yeah, this is so there are situations where we have to go beyond the complement-free values. All right. So the demand valuations, as I said, it's the case where agents want at most D items. Formally, this means that for every set X, there is a subset Y of size at most D, such that the value of X is the value of Y, right? In particular, that means that in the optimal allocation, each person gets at most D items, otherwise and weighted items, right? An important example is the unit demand valuations, where each person just wants one item at most. And the result I will tell you about is this. If we have valuations with demand of size D, there is an algorithm that just uses prices, uses balance prices idea, that gets 1/t+1 of the optimal allocation. All right, in particular, for instance, for the unit demand, that means a 1/2 approximation. And this is already beyond additive. This is not an additive function, right? Unit demand is not an additive function. So for that case, unit demand, this gives the same as the usual problem. All right, how we use here the balance prices idea. I will set the price for each item, and exactly using the same idea. An agent will come, and the agent will maximize the utility, right? Take the bundle among the available items that maximizes the utility, and the utility is the value for the set minus the sum of the prices, right? So I just put some prices for each item. And then whenever a person arrives, looks at what's available and chooses what maximizes the utility. There could be ties, and we assume the agents break the ties at the time. We only assume that the set they pick maximizes the utility. All right. So in this balance prices idea, we want to balance the revenue with the utilities. Right, the revenue is just the sum of the prices of the items we saw over the execution of the item, right? And then the utility is the excess over price, right? So now I can write the utility as the sum over all agents of the expectation of this maximization product among all items that are available when agent I arrives. This is set AI. Will maximize the I of X minus the sum of prices in X, right? So that's the utility I of X. Now here is a little trick. As in the single item case, the valuation of agent I is independent of what's available when agent I arrives, right? It only depends on previous value. So I can replace VI with an independent copy of VI. Right, let me call it VI bar. Now the I bar is independent of everything, right? So now I will lower bound this with a smaller set. So I was optimizing here over set AI, what was available. Now let's optimize over a smaller set. M minus the solved items. M minus the solved items is what's available at the end, right? Just like in the single item case, it was considered a lower bound by the probability that the item was available at the end. Here we lower bound with the set of items that are available at the very end, right? Because I did this little trick of replacing BI with B bar. Here this B bar is dependent of this other set, M minus 1. If I didn't do that, then they wouldn't be dependent. But because I did that trick, now I have B bar being dependent of what's available at the end. And then I can lower bound that optimization problem with one particular choice of the set that we're maximizing on, right? I will choose the optimal allocation, what this person should get in the optimal allocation, right? Let me call it that opt I bar. With this DI bar, this agent, if we draw everyone else's values also, this agent should get opt I bar. And I will put that there, well, only if this set is feasible in this maximization problem, right? And when it's feasible, when opt I bar is inside the set M minus solve, right? What's available at the end. So if the set I should get is still available at the end, my utility has to be at the exact, right? Because I choose what maximizes my utility. So my utility has to be at least what I will get from what's available, what no one bought. Okay. All right. So here is the balance prices. If I solve this item PJ, this strawberry, right? Someone paid PJ, but a person that comes later might arrive and they wanted this set of I, but now since we have these complementarities, maybe they get zero utility, right? They needed that element in their set. So we want to compensate for that loss, right? Then what I will do is I will set the price to be the expectation of that utility that is lost. For the set that contains the item in the optimal location, that contains the item in the optimal location, right? I will set the price to be the expected utility that comes from that set. I mean, the thought experiment is that if we did the optimal location and force the agents to pay the prices I said, this would be the utility, right? So I will set the price to be exactly that. There's a little caveat because here the P appears on both sides of the equation, right? So it's not that I can say, oh, I set P to be this because it's a bootstrap, right? It appears on both sides. But the solution is that the right-hand side is actually continuous in P, and this in a bounded set. So like Brouwer's fixed point, this equation always has a solution. So we can always set prices that satisfy this, even though like P appears on both sides. Okay, but the good news is that we have prices that balance these two things. Okay, so to finish the argument, we have the utility and the revenue. Let's say these green sets are the optimal allocation, right? Everything that doesn't touch the solved items, we do get at least that utility, right? For the green sets that touch the solved items, where these are paid for, right? That's how we chose the prices, right? For this green set here, that blue item pays for that loss, right? So that set is over there. the revenue we cover all these other two sets. So the expected welfare from the algorithm, the sum of the utility and the revenue is at least the utility for all agents in the optimal allocation, right? With this price. I here have sum over all agents, right? Before I had only the sum over agents whose optimal allocation was in the last remaining items. Right? Now I have all agents. For the optimal allocation, we have the following. We can the optimal allocation is the sum of all values, right? Now I can subtract P and RP, right? The optimal allocation says each item only once, right? So each P appears only once. So we get sum over all prices and sum over agents of this utility. And then just notice that since I'm assuming that the optimal allocation all sets subsides at most P, right? Each set appears once in each of the items, right? And on the prices part, in the revenue part, I would have many copies of the sets, but only at most D copies of each set, right? Because I mean, we think the green part is the contribution of the second term, the contribution of the blue term, the first part will be for each set, one for each item that is contained. That's it. So we get at most D plus 1 times the utility, and that is the D plus 1 approximation. Right, using those prices that we set with that equation, we conclude that we get a D plus 1 approximation. What is this? Is all right? Sure.
So where did you use the issues?
No, they're not available. No, they're not available. They're no, they're so besides having size at most D, the optimal allocation, they are arbitrarily complementary values. Yeah, it could be that the value for two items is 100 and for each item separately is 60. Right? So that's why I have to, for each item, I have to cover the entire thing here, right? Because it could be arbitrarily complementary.
And
Yes.
so the monotonicity of the dimensions or
Yeah.
I think it's not.
Maybe not. Yeah, I'm not sure. I mean, no, I guess not, because I mean it's just the maximization problem. So if it's not monotones, you take a smaller set. Okay. Yeah. So now I want to move to this other technique idea. So I mean, before moving that, maybe I mentioned one thing. This D plus 1 is type if we insist in using item prices. If we insist in setting a price for each item at the beginning of the execution and stick to those prices, this D plus 1 is the best you can hope for. I guess that's why the airline charges me 8,000 and not the same as each separate ticket. Because I mean you cannot go beyond this D plus 1 with item. Victor actually will tell you about a lower bound. I think it's square root B divided by log B, or
Yes.
so you cannot even if you do something more sophisticated online, you cannot go beyond that. So you cannot go all the way to a constant in this way. All right. The other technique I want to tell you about is this idea of using samples to protect the items. Right? The other approach was entirely based on balancing things, right? No, I don't want to balance things. I want to protect the items from being given away to everyone. And this is based on the following very simple observation. Who would win this battle? If I have a fight with myself, with an IID copy of myself, we have a battle. Who wins? If we are IID copies. With what probability the red copy wins? 1/2, right? Like their ID, so each of them is has the same probability of winning, so the probability of winning is 1/2. Right. So why is this useful? This very simple observation. Let's go back to the single item. Let's say we draw a sample from each of the distributions. Before starting the sequence, I draw an independent sample of each of the distributions. And I will set the threshold to be the maximum of these samples. All right, so I draw samples bi prime. I take the maximum of the bi primes, and this is my threshold p prime. I will allocate the item to the first person whose value is larger than p prime. That's the algorithm. Then when a person comes, has value bi, and we have to check, is the item available when this person arrives, right? So what is the event that the item is available, the single item is available when agent I arrives? Is the event that all previous valuations are below the threshold, right? Now, all previous valuations are at most the maximum valuation, right? So like all people that came before this green agent have a value at most the maximum of all agents. So we can think of the maximum of previous valuations as like, okay, it's at most all valuations. So let's think of it as just one independent copy of the maximum valuation. Because I defined the threshold in that way, maximum of the samples, the maximum valuation has the same distribution, right? So that means that the item is already 1/2, right? Because the maximum of the samples and the same distribution as the maximum of the real values. All right. So the expectation of the algorithm is at least sum over all agents of the expectation of the value of agent I times the indicator that the value is larger than the threshold, otherwise we don't allocate to this person. And no one else took the item before I, which we can lower bound by the event that an independent copy of the values was below the threshold, which you can think is just another copy of the percentage, right? An independent copy of the percentage. Then, we can exchange now T prime and T double prime, right? In the expectation. And nothing happens. So we can take the average of these two things. And we sum these two, we get the indicator that bi is larger than both, right? And now we can replace the sum with the maximum, and we get 1/6 using this algorithm approximation with respect to the maximum valuation. Actually, so this is a simple proof that gives the 1/6. Actually, this algorithm gives a 1/2 for the single item. But the proof is a bit more complicated. Okay, but the whole idea was use the samples to protect the item from being allocated to A. Notice here I never said anything about balancing revenue or utilities. It's really the idea of protecting the item with samples. Now, why is this useful beyond a single item? We can use this idea to go actually all the way to the subvalue values. Subvalue valuations are valuations such that the value for a union is at most the value of the sum, right? The sum of the values. And that, as I said before, it encodes this idea of non-complementarities between the items, right? So the evaluation cannot grow too quickly. Right? And there are different classes in there. The other one I will talk about is this XOS, substantial extraction superlative. One way of characterizing this class is the following. For every set A, if X is a randomly chosen set, not independently, just maybe correlated on the items. But it's a random set. That for every item in A contains it with probability at least alpha, then the expected value of that set is at least alpha times the valuation of A. There are more ways of characterizing this class, but this is one. If I take a random set that covers each item with probability at least 1/2, the values of this alpha times, sorry, 1/2 alpha, then the values of this alpha times that. And it's part of the superlative thing of a set that is with probability 1/2 A, with probability 1/2 B. So we recover the inequality. All right. Now, if you wanted to use the previous idea from the single item, using the samples to protect the items, we have the issue that valuations are this big list of numbers, right? Exponentially many numbers. So there is no clear value per item, right? So how do we do this idea of protecting items? For that, we need an extra tool. I call it random score generator. It's just some function that takes a valuation and outputs a score for each item. And maybe it's randomized. So it's random on top of the possible randomness of B. There might be the score might be random. So it's just a number for each of the items. And these numbers depend on the valuation. Right? But it's just some. Okay, so I will use this as a tool for designing my algorithm. One thing, I haven't said anything about how these scores look like. And it's just some function. But with that, I can design an algorithm. So the algorithm will be, I will draw a sample from each of the valuations, B1 to B prime. I will pass these B primes through this random score generator, this function. This will generate a score per item per agent. And I will take each item and I will do what I did for the single item. I will set the threshold that is the maximum score for that item. Right? Just as in the single. And then I will do in parallel the allocation for each item. If the score is larger than the threshold, I will assign this item. So it's really just using this tool of random score generator, it's really just doing in parallel what I did for the single item. Now, the reason this is useful is the following lemma. Call it the mirror lemma. And it's basically the same intuition as in the single item. The value that an agent gets with this algorithm is at least 1/2 times the expected value for the following set. The items for which the score is larger than 2 copies of the threshold. Remember, we have a similar expression in single items, right? So what is the set that the agent gets? The set the agent gets is those for which the score is larger than 1 copy of the threshold, but also we need the condition that the item is available, right? These 2 conditions. Now, what I'm telling here, I can get rid of the second part, that the item is available, by adding this other copy of the threshold here. Instead of 1 copy of the threshold being available and being available, I will remove the being available with having another copy of the threshold and losing this 1/2. And now I'm assuming the valuations are valid. So they live in one of these classes of complementary valuations. The intuition is The same as in the single item case. The set of available items are those for which the maximum values, the maximum scores are below the threshold, and the unavailable are those for which the maximum score is above the threshold, and because they are ID, right, they can exchange. So the proof is really this. So the set I is the set for which the score is larger than the threshold and is available. And being available, we can encode with this other inequality the maximum value before I was below the threshold. The maximum score below before I was below the threshold. Now I can exchange these two because they're ID. So I get the same thing. So the same thing as the average, right? They're the same thing as the average. So 1/2 times the sum of this. But because of the subadditivity, the sum has to be at least a union, right? And the union of those two things is where the score is larger than both, right? Awesome. So the great thing of this idea is that now I can get rid of this online part of the execution of the algorithm, right? The online part is that when I do the allocation, I don't know what will happen in the future. So in the future, I have to take into account that I already gave away some items. And here, I don't care anymore about that, right? I'm only caring about whether the score is large enough, right? If the score is large enough, I say with this algorithm, the agent will get it, will get this set, but only using this 1/2 factor. And notice that this doesn't require anything about how I define these random score generators, right? I haven't used anything about it, just that they are a number per item. So actually, to go to some approximation, we need to now define these score generators in some way, right? We want to define a random score generator such that the value of this set is good, right? This set here, we want it to have high value for the, right? So for that, we need to look into the random score generator. And for XOS, there is this very simple random score generator that gives a 1/3 approximation. The random score generator, remember, is a mapping from value to a score. So I will do this. For a value VI, I will sample everyone else's valuation, compute the optimal allocation, and in this optimal set, the agent I should get, I will draw a uniform 0/1 random variable for each item. Outside that, I will set all the scores to be 0. Right. We can show that this set, the one that we're guaranteed to get by the middle lemma, this set contains of I. Sorry, this set contains every element of I with probability at least 1/3. Why is that? Because the score is a uniform 0/1, and the threshold was, I mean, this is the division, it's not the but the threshold is the maximum over the score, but since we are using the optimal allocation, each item is given away only once. We are doing this independently between agents, so we might have more than one, but the expectation is at most one person that wants this item, right? So it's the maximum over, in expectation, one uniform random variable. One can show that this is stochastically dominated by uniform 0/1. So it's like having the score being larger than like a uniform 0/1 being larger than 2 copies of a uniform 0/1. This happens with probably 1/3, right? Okay, and because of like the characterization I gave you of the XOS, right? Remember the characterization was what is here, XOS. If I have a random set that contains each element of A with probability alpha, then the expected value of that set is at least alpha of the set A. And this is exactly what I just said about this set. It contains every element of I with probability 1/3. So the value of that set has to be 1/3 of the value of that. And times the 1/2 of the middle lemma, we get a 1/6 for XOS. Yeah. So I won't give the details, but there is another random score generator that for subvalid evaluations also gives a 1/6 competitive algorithm using this mirror lemma. But this function, this random score generator doesn't work because for subvalid if we have only this per item guarantee, like here, it's not enough to get the value of the entire set. But yeah, it's based on this mirror lemma idea again. Cool. So one last thing I want to say, I didn't say anything during the entire talk about computation. And I mentioned some fixed point arguments, some Brouwer fixed point theorem, and these random coordinate, these obscure objects. Can we compute these things? So to compute things, what it requires some form of succinct representation of the evaluations or some oracle access to the distributions, because there are these huge lists of numbers, right? Exponentially many. So if we want to look at this list, there's no way we can have polynomial time. So there are two types of oracles. There is the value oracle, where we ask for the value for a set. And there is the demand oracle. Sam mentioned it. This oracle is we ask for, we say these are the prices. What's a set that maximizes the utility for this value? That's the demand oracle. And as Sahil said, if one writes this LP, which is called the configuration LP, it's just I have a variable for each agent and each set. It means it's like an indicator that I give set S to agent I. And all the constraints, all they are saying is that an agent gets one set, right? The first constraint. So for an agent I, the agent I gets one set at most. And for every item J, I'm allocating the item at most once, because I said I only have one copy of each, right? So that's the configuration P. And the cool thing is that you take the dual, we get this, which has polynomially many variables, and the demand oracles are actually a separation oracle for dual. So we can solve this LP in polynomial time using demand oracles. And every time I mention the optimum in the two results, I said for instance, here I said, oh, we compute the optimum. We cannot do that, but actually for this to work is enough instead of considering opt, taking a solution for this generalization. So everything still works. Also, the other one for the demand also can be done, solving this equation that I mentioned for the price. Can also be done using the LP solution instead of opt itself. Just we only need the relaxation for the argument to work. So both the two results I told you about, they can be done also in polynomial time if you have demand oracles. Yeah, to finish this, I wanted to mention some open directions I'm excited about. The first one is I said that this mirror lemma with these random coordinators can give this 1/6 for subvalid evaluations. However, it's these obscure random coordinators that I didn't tell you, but they are based again on a fixed point argument. It's really a weird mechanism. So I would like to know what can we do if we post prices for the items. Actually, for XOX, one can do 1/2 with item prices. But for subvalid, the best we know is an order of log number of items approximation. We don't have a cost approximation using prices. And also, this is the only thing we know with polynomial time. For XOS, we can do it in polynomial time, but for subvalid, what I said, we cannot do it in polynomial time. So we don't know if we can get a constant first valid employment time. So this is an important question. Another question that is related to the demand is something that is about this class called MPHD evaluations. I won't define them because it's a bit complicated. It would take time, but it's a generalization of both XOS and D demand. For that, the best known ratio is 1/4 D minus 2. But we don't know worse bounds than the ones we have for D demand. In particular, can we get the 1/D plus 1? That's something I want to know. Yeah, another direction that people are very interested in lately is that these results are again this offline optimum, right? But in real life, maybe one don't want to approximate this offline optimum, maybe want to approximate the online optimum in polynomial time, right? Because some of these results we don't know how to do them in polynomial time. Can we approximate the optimal online average in polynomial time? Yeah, and this is very risky. Like people are working a lot on this. Every variant, there are results coming about what can we do in polynomial time against the optimal online allocation. And lastly, cost minimization. All these profit literature, profit inequalities and variance are about the maximization of social welfare, right? Sometimes we think of cost minimization as being equivalent to maximizing social welfare, but it's actually not. And we know very little in this world of profit inequalities like allocation with distributions. Even for the single item case, and even if the distributions are IAB, a constant for cost minimization is not possible. And the example is very simple. If we have two agents and they have a cost that is drawn from something called the equal revenue curve, which is the distribution that is 1 minus 1/x. The probability that the value is below x is 1 minus 1/x, right? The expectation is infinite, but the minimum of 2 copies of this is finite. Right? So with another algorithm, we cannot get anything finite, whereas the expected minimum is finite. So there is no constant possible for the single item IID. So I think we should look more into this cost minimization. The typical revenue plus utility approach doesn't work. And we have to actually figure out what is the correct model or extra, because I mean it's not possible that for the single item IID you cannot pick a cost. Okay, yeah, thank you. I'll finish.
I missed, what are you minimizing?
Oh, so each person comes with some random variable, which instead of a value is a cost. It's like, I don't know, think of procurement. Like I want to do a procurement for a project. I go to 2 different contractors. They tell me, give me a quote. I want to choose one, right? So I either pick the first one or the second one. I cannot go with 0. Right? And even with 2, you cannot get it. So yeah, completely out.
Imagine for his procurement, okay?
Yes.
When you said that, okay.
Yeah, procurement, like a procurement. Yeah, procurement option. Yes.
Very forward, do you want to maximize the social welfare? But what if instead you replace this metric with like what I remember to be national social welfare, where instead you take the multiplication of the valuations instead? For example, or like or you maximize the minimum.
Yeah. Yeah, I don't know much, but I would say the problem is that well, in social welfare, if someone gets nothing, its value 0 is not that harmful, whereas in the national social welfare, someone gets 0, it's a big problem because it becomes 0. I at some point thought a bit, you could think of the product of the expectations instead of the expectation of the product. For that, you can do things. Actually, there are some techniques where you can get an approximation for each person at the same time. And for that, you get an approximation for the social welfare. But yeah, again. don't know if someone else results for that.
Yes, but I think generally pure approximation, it is standard like okay, some of the logs is basically some kind of natural superposition. But then approximation factor and anything you're assuming about some modularity and all that should be changed. Like a factor 2 approximation in the log world is not the same as like the natural approximation. But there are some recent work about this. I think a soda paper of SIG. Yeah, SIG from Color and so on. It talks about like some online notes with some prediction, like some other models. Not they have to make further
the pricing, approach instead of prices. And that's varies for everyone. But in theory, definitely you can update the prices.
Yeah. So usually when you can adapt the prices, you can get better results. Yes. Now here for this D demand, this D plus 1 is the best you can go if you have fixed item prices. If you can update them, I don't know what's the best. Is still D plus 1 the best, or Victor, we may talk about this tomorrow. So
I have a similar question. When you say that you like to do pricing, so you mean item price or even bundle pricing?
oh no, okay. I mean fixed per item price.
Fixed per item, but if
Yeah, the first question is about first fixed per item price.
with bundle pricing.
With bundle, okay, so when with bundle prices that you can, if you can price each possible bundle and you can adapt the prices over time, you can actually get the best online average. Because there is something called the BCG payments, which is like you can encode like the loss in value in the entire future exactly, and force each agent when they maximize utility to choose the optimal decision, to make the optimal decision for the entire problem. And then with those prices, you can get the optimal online. So there is a way of like if you can update the prices and you can price every possible bundle, then you can get the optimal online. But here my question is, can you do it with a simpler pricing? Approach like per fixed per item.
Hopefully static.
Starting
Static.
per item. That's my question. All right.
Yeah, I mean, because the plenary talk is in 10 minutes. So
Yeah.
take a short break.
Yeah.
Thank you.
Yeah.